Hi, welcome to another in my series of videos where I attempt to build experiments from this book, Make Electronics by Charles Platt. So I'm not showing you how to build them, that's all in the book if that's something you want to do. All I'm doing is demonstrating my builds and what I've been able to observe from them. So far in the book, the circuits that we built have all been designed with the purpose of simply demonstrating the characteristics of various components. But now we've got to the point where finally we're able to build a circuit which actually does something in its own right. So let's have a look at that.
So excuse the darkness, but I've turned the lights down just so that you can more clearly see what happens when I activate the circuit. So I'm just going to push the button here and you can see that what this circuit does is flashes between two LEDs. Now, if you've dabbled with digital electronics at all, at this point, you're probably thinking, so what? Because flashing LEDs on and off is one of the first things that you do in digital electronics. But one thing to bear in mind here is that this is a purely analog circuit. There is no Arduino or Raspberry Pi controlling things behind the scenes here. Okay, let's turn the lights back up and then we can have a closer look at the circuit. So basically, this circuit is composed of two halves which are the same, and I'm ignoring the very first bit here, which is just a button to interrupt the power supply, or rather to connect the power supply to the rest of the circuit. But beyond that point, then each side is the same, both in terms of its layout and in terms of the nominal value of the components. I can't claim that it's identical, of course, because the actual component values will, of course, vary slightly. But to all intents and purposes, each side is the same. And the key thing is that each side of the circuit is equal. There isn't one that's primary and one that's secondary, or one part that's a controller and the other part is just responding to instructions. They both do the same thing. So how is it that when we activate the circuit, they somehow coordinate with each other to share the limelight, as it were, to decide that at this point in time, my light's going to be on, and then I'm going to hand over to you and your light's going to be on. So we can look at the circuit to get some clues about this. And one thing to notice is that the path through the LED on each side is also passing through the collector and emitter of the transistor on that side. And what that means, if you recall our previous experiment with transistors, is that the LED will only conduct and therefore will only light up when the transistor is on, i.e. when there is sufficient base current to allow current to flow from the collector to the emitter. The other thing to note is that we have a ceramic capacitor on each side. And the capacitor lead that's on the negative side of the circuit is also connected to the base of the transistor on the opposite side. And that is key to this circuit's behavior. To see more clearly what's going on, it will be helpful to hook up the oscilloscope. So that's what I will do now. Okay, so what I've got here is the probes for the oscilloscope connected to the left and right sides of the first capacitor. And when I activate the circuit, let's see what we get. So I'm just going to freeze that. So what we see here is we see the capacitor charging. It's starting from a negative voltage, which we'll come back onto, but we see it charging until it reaches the point where there's enough bias to switch on this transistor here, that will of course switch on this LED because now it has a path through the collector and emitter of that transistor. But then we get to a point where there's this horrendous crash back down to a negative voltage, which will of course then switch the transistor back off. Now, to understand what's causing that crash, what I'll do is I'll just transfer one of the probes to the other capacitor. So let me take this off here and pop it on this one. Let's just try and do this without pulling it out of the circuit board. Okay. Now let me start up again and start again. So what you can see here is here's the second capacitor charging up until it reaches the point where it has sufficient bias voltage to turn on the opposite transistor, which will of course light this LED, and that is the point that we're getting the crash on the other capacitor. And the reason that's happening is because as soon as we switch on this transistor, there's a path for this capacitor to discharge, which of course turns off the current to the base on this transistor. So at the same time as this LED is being lit, this LED is being unlit because there's no longer a path for the current flow. And so you can see how between the two of them, they kind of flip-flop backwards and forwards between those two states. Okay, so we've got our light flasher. Now it's time to add some sound into the mix. So the book asks you to build a second circuit just below the first, which we have here. And effectively, this is just a repeat of the circuit at the top of the breadboard. Two things have changed. One is that the frequency generated by this multivibrator, as you can see, is quite low. That's not going to be within an audio frequency range. So the component values for this multivibrator have been changed to generate a much higher frequency that will be within an audio frequency range so that we can hear the signal from the speaker. The other thing that's changed is you'll notice that there's a third transistor down here. And this transistor is operating purely as an amplifier. And basically the path through the collector and emitter of this transistor comes directly from the positive power supply and then goes via a current limiting resistor into the speaker and then back to the negative power rail. And you can see that just for this purpose of this experiment, I've just connected the speaker with test leads. So the multivibrator is generating a signal which is effectively being fed to the base of this third transistor. So what this transistor is doing is effectively amplifying the signal that it receives at its base. And if I depress the button to activate the circuit now, what you will hear is just a reasonably pure tone from the loudspeaker. Now that's not particularly interesting, so the next stage is to see what we can do to make a more interesting sound. Okay, so another small modification to the circuit, which is to add another transistor, and this one is bridging the two circuits. So you can see we're taking the signal from the base of this transistor on the flasher circuit to the base of this new transistor. So the collector of this transistor is being fed from the power supply to our lower circuit, and then the current from the emitter is feeding in to one side of our lower multivibrator. So what does this mean? Well, if I activate the button for the top circuit, you can see that operates exactly as it always has done, to just flash the two LEDs. If I activate the bottom button, we get our simple tone as before. But if we combine the two, we get a siren effect. So why is that happening? Well, effectively, what we've done here is to connect the top multivibrator to act as a low frequency oscillator for the lower multivibrator. So the lower multivibrator here is generating a tone at a single frequency, but then we're combining that with the signal from the upper multivibrator, which is at a much lower frequency, which is giving us that change in pitch that we're hearing. Let's just demonstrate that one more time. So you can see how those two combined are having that effect. So another small modification, this time to connect a couple of electrolytic capacitors, they're both 47 microfarads, across the two transistors in the upper multivibrator. And you may recall from an earlier episode that another thing we can do with capacitors is to use them to smooth the signal. And that's effectively what these two capacitors here are doing. So if we activate the upper circuit, you'll notice that the two LEDs, rather than going from completely on to completely off, are now fluctuating smoothly between those two levels. And indeed, this will also have an effect on the audio output if we activate the lower circuit. Hopefully you can hear how that tone is now rising smoothly. A further modification suggested in the book is to add a third 10 nanofarad capacitor across the collector and base of one of the transistors in the lower multivibrator. And what that does is brings our siren sound to the higher pitch that's more like a bird tweet, like this. Okay, the very final modification, I promise, is the previous circuit was wired up in something that's called common collector mode. But there is an alternative way we can wire it up, which is what's shown here, which is common emitter mode. And so what's happened is before, on this amplifying transistor, whereas the collector was wired directly up to the positive supply rail, and then the emitter was wired via the loudspeaker to the negative supply rail. Here we've effectively done things the other way around. So now you can see the emitter has a direct connection to the negative supply rail, whereas the positive supply rail comes through the current limiting resistor, through the speaker, and then into the collector. Why would you wire it up in that way? Well, the answer is that you actually get higher current through the speaker that way, but at the expense of a greater drain on the battery. So if I activate the circuit now, you might not be able to detect much of a difference on the video, but it is a louder sound out of the speaker. But we will drain our battery a lot faster as a result.
I hope you enjoyed that. Everything that we've built so far has been assembled either by hooking components together with test leads or by using a breadboard. But of course there will come a point where you want a circuit to be a little more permanent than that. And that's where the art of soldering comes into play. And that's something we'll be looking at in the next episode.